So let's talk about dimensions. So recall we have considered subspaces. Okay. So if you have a subspace W of Rn, we've seen there might be many different representations of the same subspace. Okay, and this is something which we encounter very often in mathematics, namely that one mathematical object has many different representations. So to distinguish objects, we usually look for some labels we give to this mathematical object, so-called invariant, which doesn't depend on the representation. So we know if we have two different subspaces, for example, and they have a different label, a different invariant, then they are different, okay? And the easiest notion is of an invariant is just a number, okay? So we have a mathematical object and we associate to it an invariant, for example, a number. And for subspaces, this invariant we will consider is called the dimension, okay? So let's consider an example. So let's consider the following subspace W. So if you don't see that this is a subspace, I encourage you to do this as an exercise, but we have actually seen this subspace on the third quiz. So the subspace, which is all the vectors of the form 1s plus 4t, 2s plus 5t, 3s plus 6t, where s and t are real numbers. There's a subspace of R3. Okay? And what is this? Geometrically, it's a plane. Namely, it's a plane x minus 2y plus z equals 0. Okay? So because it's a plane is a two-dimensional object, we think the dimension of this should be 2. And indeed, we're going to see the dimension will be 2. But we have to give a mathematical definition of what we mean by dimension, okay? So the definition of dimension. So first we have to make the following observation. It's actually a theorem in the book. I won't go through the proof, but let me state it. So let W be a subspace of Rn, and let B is a set consisting of vectors W1 until Wk, so k vectors, be a spanning set of W. In particular, this means it contains k vectors, okay? Then any set of k plus 1 vectors in W is linearly dependent. Okay, so we can slightly improve this. We can reformulate this. Any set with m vectors where m is greater than k. So any set with m vectors where m is greater than k in W is linearly dependent. Okay? So I encourage you to look through the proof in the book. The idea is you just, because it's a spanning set, you can expand every vector into the set. So you expect your k plus 1 vectors into the set, and then you're going to see that there's a linear dependence. Okay? But the immediate corollary of this is the following. Let's assume W is a subspace of Rn with a basis consisting of p vectors, then every other subspace also consists of p vectors. So let W be a subspace with a basis consisting of k vectors, then every other basis of W also has k vectors. So in other words, the number of vectors of a basis is invariant of the basis. So it's independent of the basis. It's an invariant of the subspace. Okay? It's independent of the basis. It's an invariant of the subspace. So we give it a name. We call this the dimension. So let's write this down as a definition. So let W in Rn be a subspace if the set B W1 to WK, consisting of k vectors, is a basis of W, then we say that W has dimension k. And we will also write dimension of W equals k. Okay, so that's our definition. So given a subspace with a basis, the number of basis elements, the number of vectors in the basis, we call the dimension of the subspace. And our corollary says exactly that it doesn't depend on which basis we choose. Okay, so that's a nice and important invariant of a subspace. Okay, so let's go back to our example. So we had this subspace, okay? So we can ask, what is the dimension? Okay, so we have to find a basis, but we essentially already given a basis. So what is the basis here? I'll give you a second to think about it. So a basis here is the following. So W has as a basis the vectors 1, 2, 3 and the vector 4, 5, 6. So what does it mean? So these are two vectors, right? 1, 2, 3, 4, 5, 6, two vectors. So that means the dimension of W is 2. Okay? So in other words, if you want to calculate the dimension of a subspace, you have to find a basis and then just count how many elements there in the basis, okay? So I think that's enough about the definition of a dimension. So let's make a short break here.